Hi and welcome to this new Shroom Lab video. So this video is mainly a math video, but don't worry, all the foundations you need you will get in the beginning of this video. So this video is in its core about how far can we actually move in our expanding universe. I make a lot of simplifications, but still it's a quite interesting mathematical journey to go there. At the beginning, however, we will start with something totally different. The fundamental concepts of mathematics I'm going to use in this video, I'm going to explain to you using some famous historical paradoxa. The first one is Zeno's Paradox, and it's quite well known. You'll find a dozen of YouTube videos about it, and it's very easy to understand. So here is a little roadmap of what we are going to do today. As I already said, I start with the easy introduction about Zeno's paradox. Then we're going to have the turtle on the rubber band, which is also a paradox, but only on the first glance. And finally, we'll have the turtle and the expansion of the universe. So in some of the slides you might notice this little turtle crawling around. And unfortunately, they were originally supposed to crawl around every slide, but they messed with my animations. Let's begin. So in the first introduction, imagine we have a turtle and a rabbit, both sitting on a line, and if I press play, they both start moving. Of course, the rabbit is faster than the turtle. And we see the turtle has no chance. The rabbit just is faster than the turtle and runs away. So let's get to the actual paradox of Zeno. Before we go there, just a little annotation. In this example, the turtle speed will be 1 unit per second, and the rabbit speed will be 2 units per second. So a unit can be any length, and I just enumerate them from 1 to wherever I need them. So in the end, the rabbit is twice as fast as the turtle. This ratio will become important later. In Zeno's paradox, the turtle is allowed to have a head start over the rabbit. In this case, it's a head start of exactly 1 unit, or 1 second. And what's the actual paradox about this? But before I come to this, I will first say that it's important to understand that 1 unit head start is equal to 1 second head start. I mean, the turtle moves 1 unit per second, so if you give it a 1 unit head start, it's the same as if it just moved 1 unit. The actual paradox is that while the rabbit is catching up to the turtle moves a little bit more. And this little distance, the rabbit has to catch up again, but on the other hand, the turtle moves again. And this can happen infinitely many times. And the thought Zeno made in the ancient Greece, that the rabbit never catches up, because he has to infinitely often catch up, and always the turtle makes a little more progress. So let's view this in our example in a little bit more mathematical approach. If the rabbit catches up, there is a time t catch. So here we didn't dissolve anything of this paradox, so t catch might be infinity. The rabbit needs half a second to get to the position where the turtle started. I mean, he moves 2 units per second and he has to move 1 unit, so he needs half a second to catch to the first position. But in this time, the turtle moves with 1 unit per second in half a second time, half a unit. For this, the rabbit needs 1/4 of a second to get to the second iteration position of the turtle. So if we do this n times, In the nth iteration, the rabbit needs 1 divided by 2 to the power of n second to catch up. The time the rabbit needs to catch up with the turtle is the sum over all iterations. So every iteration with its 1 over 2 to the n time. We sum that all together, we get t catch. Note here that we have infinitely many terms we are summing up, and he can only catch up if the sum is a finite value. And basically the key insight here to resolve the paradox is, if you have infinitely many elements that are summed, the result might be finite. And as a little addition, it's 2 to the power of n because the ratio of the speeds is 2 to 1. If we would change them, we would get a different basis below the exponential. And if you just have them at the same speed, it would be 1 divided by 1 to the power of n, which is simply 1. And the infinite sum over 1 would not be a finite value. So the question is it a finite value if we have 2 to the power of n? Now we just take a look from a different approach. I first play the animation I didn't play in the beginning, where you can see that the rabbit actually catches up and is even faster than the turtle at the end. So we see from this animation that the series has to converge to a finite value. So converging means that once you go to infinity, you get a finite value. But the question is still, how can we show this mathematically? The simplest approach is to model the progress of both the rabbit and the turtle, so the units they made in respect to the time as a function. For the rabbit, this is 2 times t. So after 1 second he made 2 units, after 2 seconds 4 units, after 3 seconds 6 units, and so on. For the turtle it's 1 times t, since it moves with 1 unit per second, and 1 for the head start. If the functions intersect, the rabbit catches up. And they do intersect at t equals 1. You can just subtract t from both sides and then you get t equals 1. And this proves the convergence of the geometric series, and that's how the series is called. So 1 divided by q to the power of n and the sum over this is called the geometric series. And we actually found a way here to calculate the value they converge to. This will be important later. And they always catch up at some point, as long as their speed is not equal. That's also quite an interesting insight. So now you have made it successfully through the first part. We start now with the second part, which is also, on the first glance, a paradoxon. Like with Zeno Paradoxon, it is actually not a real paradoxon, since the solution makes sense and there is just one. It's the same here, but it's a bit more difficult to get through it. So we have again a turtle, but no more rabbit. So we imagine the turtle sitting on a 1 unit long rubber band, and it moves with 1/10 of a unit per second. So obviously it needs 10 seconds to the end. So I force you now to wait 10 seconds until the turtle made it. But we are not that nice. We are going to stretch the rubber band with 1 unit per second. So the size of the rubber band over time equals t, meaning that after 1 second it is 2. Okay, that's actually a little mistake. It should be t plus 1. Because at 0 it's already 1 length. So after 2 seconds it should be 3 long, after 3 seconds it should be 4 long, and so on. Well, it is a little mistake, but it shouldn't bother us too much in the presentation here. You guess what I mean. It's just 1 unit longer every second. And the question is, will the turtle make it to the end? The band gets stretched 10 times faster than the turtle moves. Remember, the turtle moves at 1/10 of a unit per second, and the band is expanded away from the turtle at 1 unit per second. I have put this in perspective here. We start with a 1 unit band and the turtle sitting exactly on the beginning. Then, after 1 second, the band is twice as long and the turtle made 1/10 of a unit progress. And after 2 seconds, the turtle made some little more progress and the band is now 3 times as long as in the beginning. Doesn't look that promising for the little guy. So to get to the point, let's look at the relative distance the turtle travels at 1 iteration. So in the beginning, the relative distance in 1 iteration, which is equal to 1 second, was 1/10 of the whole rubber band. So the relative distance is how many percents of the total rubber band did the turtle travel in this iteration. Turtle moves with 1/10 unit per second, and if we have 1 unit size, that's just 10%. If we have 2 unit size, that's 5%. If we have 3 unit size, that's around 3.3%. And with n unit size, we have 10% times 1 divided by n, which is equal to 1/10 times 1 divided by n. So 10% is actually the same as 1/10. The same as 1% is the same as 1/100th. And as 100% is the same as 1. That's just another way to express relative. And it's very important, relative. So no matter how long the rubber band is actually in units, 1 is always the end, and 1/10 or 1/20 or 1 divided by 10 times n is always the distance, the relative progress the turtle makes in this iteration. So we normalized it somehow that the length is always 1. And the progress is relative to this. The key insight in this paradox is that the relative or percentual progress of the turtle that it has already made doesn't change as the band is stretched. And that is because the band is stretched the same way behind the turtle as it is in front of it. So that if the turtle would sit exactly in the middle and we stretch the band by a factor of 1000, it will still sit in the middle. So the total relative progress of our turtle after n iteration is the sum over 1 divided by t, where t is the iteration. And the 1/10 is usually inside of the sum, but because of the distributive law, we can just pull it out and write it in front. And the big question is, will it get larger than 1? Because once it reaches 1, we are at 100%. That means we are at the end of the rubber band. And of course, n should be finite, so that there is a finite time the turtle will make it. And as it turns out, in Zeno's paradox, the series converged, the geometric series. This one is called a harmonic series and it does not converge. So it goes to infinity, which in the end means that no matter how slow or fast the turtle moves, it will always be some point in time where it gets larger than 1, because the right side can go up to infinity and compensate any slow value on the left side of the product. Remember the function s from t equals t plus 1, just think about that here, which is the total length in respect to the time. we can also write p from n, so the progress from time or iteration. Here it is p from n because this is fold in iterations, but it could also be p from t because we could do this with time. So we have 1/10, which is turtle speed times the sum over 1 divided by s from t, where s from t is the total length at number t. So we are summing up all time steps till the iteration we are currently on, which makes perfectly sense. What if we stretch 2 units per second? So we're just a bit faster at stretching. S from t equals 2t. Well, then we can insert this into this formula, take out the t, and we see it's equivalent to just a slower turtle. So of course it will still make it. We still have this divergent series, the harmonic series on the right. Just the turtle is half as fast, but no matter, we said, it doesn't matter how slow it is, it will always make it. But what if we stretch it faster every second? So we stretched it 1 or 2 units per second, but what if we at some point just decide, well, now we stretch it 3 units and in the next iteration 4 units and so on. An example for this is t squared. Because the speed we stretch at the second n is 2 times t. So don't get confused here. The length after t seconds of the rubber band is t squared. However, the speed we stretch from the nth iteration to the nth plus 1 iteration is 2 times t. Well, I again see that I messed up n and t. But you can think in this presentation that n is the same as t. So this makes no difference. N is the iteration step and t the second, but both are describing the same here, since we selected one iteration step to be 1 second. And as it turns out, it is the derivative of the total band size. So up to now, we always had a constant derivative. And this resulted in a linear function that describes the band size. Now we have a quadratic function describing the band size, and therefore a linear derivative. So let's insert it into our formula. Once we put t squared in there, this expression converged. And more precise, if we take 1/10 into account, which is the turtle speed, it converges to pi squared over 60. So this means even for an infinite amount of time, the turtle will never make it to the end of the rubber band. However, if the turtle is faster, it might still make it. And you see, the turtle does not have to match the speed the rubber band expands. A velocity of the turtle of 2/3 units per second are enough to make it to the end of the rubber band, although the expansion speed is quadratic. So there's still hope, but only for the faster turtles. The slower ones, they won't cut it. So we can come to the conclusion that if the speed we stretch the band is constant, lowering over time, the turtle will make it at every speed. In all the other cases, the turtle can make it if the speed is high enough. And finally, we might think, what happens if the turtle accelerates or gets out of breath and then decelerates? So then we also have a turtle speed, v of t, which changes over time. And so our progress after n iterations is basically the sum to the nth iterations over the turtle speed times the size of the rubber band at this point. And this is just a larger series. We need to check if there's an n so that it's larger than 1, and maybe it converges or it doesn't. Now we come to the final and, in my opinion, most interesting part of this video. Our universe is expanding. You hear it everywhere. So if we start today, what is the most distant point in universe we can reach if we travel at the maximum possible speed of light speed? I mean, we will never travel at light speed, But in this video we do have the space turtle and they can do that. Also it's interesting because the light we send out travels at light speed, and we can see what's the most distant point in the universe now where you could ever observe us. So if you are now beyond this border, you will expand that fast away from us that you will never see that we are even existing. So if there is intelligent life out in the universe, it has to be somewhere inside of this region, and we are going to find it. The universe expands, which means that if we are sitting somewhere in the universe and like the rubber band it's pulled apart, all objects move away from us. Because as you remember, the things behind us are stretched and the things in front of us, only our position stays the same in our view. And the more distant, the faster it expands away from us. That's just the nature of expansion. And this relationship is almost linear, and it's called the Hubble parameter. This constant or parameter h is 70 kilometers per second per megaparsec. A megaparsec or parasec? I don't know. I guess it's parsec. Megaparsec is just a long distance. So if you look at this expression closely, you see 7 kilometer divided by megaparsec. That just could cancel out, which would make no sense anymore. So you could theoretically convert the 70 kilometers to megaparsecs, and it gets to a really little number, a really small number. We will do this later, so you will see this. And this expression actually means an object that is n megaparsecs away moves at 70 times n kilometers per second away from us. So 70 kilometers per second is quite fast. And imagine it's 10 megaparsecs away, it moves 700 kilometers per second away from us, which is just incredibly fast. And in this example, we assume that h is constant and never goes away from 70. However, in reality, it's expected to lower about 10% or even more, and finally converge to something like 50 or so in the future. I'm not really deep into that, how it will converge and what are the best estimates, but for this example this would just be too much. And now you might say, well, I've read the universe is expanding faster and faster over time. How can h be constant then, or even shrink? Well, you're gonna see that now, because a being constant does have nothing to do with the total size of the universe in the way you're expecting. Oh, the colors messed up. Yeah, that's totally part of this presentation. So consider the end of the gray line a 1 megaparsec distant star. So I'll have to get my mouse in to show it to you. Here is the end of the gray line, and there is the end of the gray line, and here is no blue line attached. So we'll start here. And for simplicity, we set h to 1 megaparsec per second and megaparsec. So in the beginning, we have a 1 megaparsec distance, which is this gray thing here. And the blue is the progress that is made by expansion after this iteration finishes, which is also 1 megaparsec per second, because we are 1 megaparsec away, and we have 1 megaparsec per second per megaparsec. So being 1 away, we just have 1. Then, in the next iterations, we have now the one from the beginning, and the one is expanded together, which is 2 megaparsec away now. So the distance it's going away now is 2 megaparsecs per second, because we are 2 megaparsecs away, and 1 megaparsec per second and megaparsec. So we have to take it times 2. So the blue distance that is being added is now 2 megaparsecs. The next iteration, we are already 4 megaparsecs away, and again the blue thing which would be added here would be 4 megaparsecs. So we would go from something like 1, 2, 4, 8, assuming a constant h parameter. And like with the rubber band, we define the total size of the universe over time as s from t. So s from t is basically the size function. In our example, s from t plus 1 was equal to 2 times s from t. And this is a recursion formula, and if you solve it, you get an exponential function. S from t equals 2 to the power of t. And there we have it. A constant h results in an exponential growth of the universe size. So it's actually faster and faster over time, and even the derivative is an exponential function, so it's really expanding faster and faster in an incredible fast way. So just for a little exercise, you could work out how the Hubble parameter has to change if you want a linear expansion of the universe. So then it obviously can't be a constant. It has to shrink with a certain function. So by taking the current value for h and assuming that it is constant, we can make this function size from n, which is the iteration, and d, which is the distance. Because obviously this size is different for different distances in the universe. And in this distance we later apply the star or the galaxy or wherever we want to move to, and then we'll look, while going with the n iteration upwards, if we are able to get above 1. So d is the current distance to the target, and n the number of seconds. And s from d gives us the new distance. And we can insert this into our formula. C is the light speed, so we are moving at light speed. And we check here for the space turtle if we get this sum larger than 1. And in this case I'm very generous. I allow infinitely long trips, so n can go to infinity. So that means if we still, with an infinite long trip, can't get to the target, then we really can't. So even with infinite time and light speed, that's really the maximum I can throw in here. It also simplifies the equation. So we are adding the formula in from above, and maybe a little explanation of the formula. I just pulled the 1 over d out, and d times, so d is the distance it's now, and we take this times 1, so the distance that is there now will be also there after expansion, plus d times the Hubble constant to the power of n. So we are just looking after we did n of these little progresses, and they always kind of accumulate on each other in the exponential way I showed at the beginning. So this is just a formula I derived from the example 3 slides ago. And once we inserted it below, have the sum to infinity, we can now use our knowledge of the geometric series. Because guess what? This is a geometric series like in Zeno's paradox. So now we have it. You have the series from Zeno's paradox, and you have the formula that tells you how you have to use the size function from the rubber band of the turtle. And all combined, we can now use our knowledge to check how far we can get. We already know how to find the limit by intersecting lines. You can try this for yourself now and stop the video. Or you can just look it up on Wikipedia and feel good afterwards. Since n is approaching infinity and we resolve the equation, we will only have p from distance. And if this p from distance is larger than 1, we can reach our target. Otherwise, it's impossible, even for our space turtle. So let's visit our closest galaxy. I mean, the closest star would probably be too boring, it's just 2 light years away. We certainly do it. But Andromeda is 2.6 million light years away, which I approximated at 1 megaparsec here. So this approximation is really bad, but all the other approximation, like this incredible large number that I've told you earlier of, which is just 70 kilometers divided by 1 megaparsec in kilometers, which is just absolutely, which is just 70 kilometers in megaparsec, so it's just absolutely useless. It's so small, there's so much error in it, and it basically has no point to do anything accurate here. And the final thing we have to do is we have to write c, the light speed, in megaparsecs, so that all the units cancel out equally. So c is around 9.71 to the 10 times 10 to the minus 15 megaparsecs per second. So in megaparsecs the light speed is actually quite small. And let's insert this and we get around 4,000%, which is definitely more than 100. No, we get 4,000, which is 400,000%, which is definitely more than 100%. So we, no matter what, we definitely will reach Andromeda, our neighboring galaxy. So the next thing we could probably look at would be something like the local group of galaxies that we want to go to the neighboring group. So in fact, there's a nice graphic, and I'm going to show it to you soon. So the largest distance we could ever go to is to the neighboring supercluster. No idea if you've ever heard of this, but you'll see soon. There we have it. I have to add that in reality the turtle might make it a little bit further, since age is lowering a bit during its journey. As I explained, it's expected to lower 10%, but for this simulation and for this run here, it really doesn't matter because it would make things complicated. So I get my mouse back in. On the really left side we have our Earth and our Moon. Inside of our inner solar system, that's the asteroid belt somewhere here, the outer solar system, and this is located somewhere in the closest stars. We can all reach that, which is located inside our Milky Way galaxy. We can go everywhere we want in our galaxy. This is located in a local group of other galaxies, and we can reach every other galaxy in this group. Somewhere there is also Andromeda. This is located in something called Laniakea. No idea how to speak that, but these are multiple groups of galaxies that are somehow clustered together. We can go everywhere where we want. And of these Laniakea clusters, there are multiple clusters. And now it comes to an end. In this model, the furthest we can go is the blue circle, which are only our neighboring clusters. But we can't go to these clusters of galaxies here. They have also, every one of them has groups and galaxies and stars and solar system and planets. And in the observable universe, it doesn't even make that much point. The circle would be much smaller. So a really large point of the universe, according if this model here, if we take this as a basis, we cannot visit at all. And there's one thing I like to mention at the end of this video. It might also happen that on halfway you notice that a distant point is too far, or that your calculation had some errors. And if you're really unlucky, you can not only reach that point in no future, but it's also too late to go back, because it has expanded too far away from you as well. So if we are really unlucky on your space travel, you might get stuck in the middle of nowhere, with no chance to escape. even with light speed. No chance, even if with infinite time. So if you would make a flashlight on in this region of space, no one would ever see the flashlight again. Not even you. Goodbye.